Welcome to this explainer. Today we're going to do something a little bit different. We're looking way past those shiny finished skyscrapers, the pristine highways, and the modern bridges. Instead, we're going straight to the source to unpack the massive physical reality of how our modern world is actually built. We're diving deep into the operational footprint of construction materials, using the comprehensive framework laid out in the SASB Sustainability Accounting Standard. I mean, just look around you for a second. Almost everything you see in our built environment started as raw earth. The sheer, massive physical volume of stone, sand, and petroleum required for global infrastructure is honestly staggering. So the big question we're tackling today is, what does it absolutely take to physically excavate, crush, and combust those elements? What is the true on-the-ground footprint left behind by the companies that literally move mountains to build our cities? To really understand this, we have to look at the core operational model of this industry, which is kind of this fascinating dual reality. On one hand, materials producers are basically miners. They operate their own massive quarries to extract crushed stone, sand, and gravel directly from the earth. But they definitely don't operate in a vacuum. To process all that heavy material, they rely heavily on purchasing massive raw inputs from outside sources, specifically fuel and chemicals from the broader mining and petroleum industries. So, balancing this extraction of the earth with the consumption of external fossil fuels is really the defining challenge of the sector. Just picture it. On one side, companies are directly mining the physical bulk of products like cement and concrete. And then on the flip side, huge amounts of petroleum and external mining products are piped right in to literally fuel the fires of their operations. It's a massive input-output equation. Part 1, energy, air, and emissions, the kilns and the atmosphere. When you're superheating rock to make something like cement, the chemical reality of that process is incredibly gritty. The SASB standard actually tracks a highly specific and, frankly, a pretty overwhelming list of hazardous air pollutants. We are talking nitrogen oxides and sulfur oxides, fine particulate matter, complex stuff like dioxins and VOCs, and even heavy metals like lead and mercury. It's vital to get a real visceral sense of this list, because these emissions carry severe localized health impacts, not to mention exposing producers to some major regulatory risks and compliance costs. Now, to reach those extreme temperatures, these operations require an absolute ton of energy. And here's where it gets really interesting. Beyond just using grid electricity or renewable energy, producers often power their kilns using alternative fuels. To lower costs and manage waste, these facilities will literally burn scrap tires, spent solvents, waste oils, and even agricultural waste, like peanut shells. It's a highly industrial form of recycling for sure, but one that demands incredibly strict management, so they don't accidentally release all those hazardous pollutants we just talked about. Combusting all that fuel, whether it's petroleum or millions of scrap tires, combined with the chemical reactions of processing the stone itself, naturally generates a colossal amount of greenhouse gases. The industry standard mandates the tracking of what's called gross global scope 1 emissions. These are the direct emissions coming from the stationary kilns, the mobile heavy machinery rolling around the quarries, and the actual chemical processes. And because this industry is just so carbon intensive, these direct emissions leave producers hugely exposed to financial risks from things like cap and trade regulations and carbon taxes. Part 2, land, water, and waste, shaping the earth. Okay, let's bring it back down to the ground. When you operate a quarry, you are fundamentally altering the landscape. You're removing vegetation, you're blasting rock, and you're displacing wildlife. That is exactly why the SASB framework zeroes in on the terrestrial land area disturbed, and crucially, the percentage of that land that is eventually restored. And restoration, by their definition, means assisting the recovery of an ecosystem that has been degraded or destroyed. It's not just about filling a giant hole back up with dirt, it's about genuine ecological recovery. That is a massive reputational and regulatory requirement today. You see, an environmental management policy can't just magically kick in at the end of the project. It has to span the entire life cycle. That means starting way back at pre-bid and appraisal to figure out if a site is sitting in a critically sensitive habitat, all the way through site development, active production, and finally closure and restoration. At every single one of those stages, companies have got to manage biodiversity impacts, noise pollution, and waste generation. Otherwise, they're looking at fierce community resistance and heavy legal liabilities. And it's not just the land. Processing these heavy materials requires absolutely massive volumes of water. And we have to distinguish between water withdrawn, which can potentially be returned, and water consumed, which is permanently lost to evaporation or physically incorporated right into the product. The real risk hits hard when this massive consumption happens in regions facing high or extremely high baseline water stress. Imagine doing this in a drought-stressed area. Competing with local communities for drinking water can lead to immediate production shutdowns and soaring acquisition costs. Then, of course, there is the physical waste left behind. While most of the rock gets used, those air pollution control devices we mentioned, the ones capturing the toxic emissions, well, they generate a byproduct called cement kiln dust, or CKD. It's this fine-grained, highly alkaline solid waste. Managing, safely storing, and trying to somehow recycle this CKD is honestly one of the biggest regulatory headaches in the entire industry, simply because improper disposal can cause severe environmental contamination and spark massive lawsuits.
Part 3. Workforce Health and Safety, the Human Cost.
We have to remember the people doing this work. Operating heavy machinery, blasting rock, and breathing the air in these hazardous quarry environments comes with an incredibly acute human cost. One of the starkest, most sobering metrics tracked by the SASB standard is a count of reported cases of silicosis. Silicosis is a chronic and often fatal lung disease caused by inhaling microscopic crystalline silica dust during the rock crushing process. Tracking this specific metric is absolutely vital because it isolates a severe occupational health risk that demands rigorous respirator programs and relentless safety compliance to protect workers' lives. And beyond that long-term exposure risk, there's just the daily physical danger of the job. Heavy industry relies a ton on contractors. Because of that, companies are required to track safety metrics, specifically the total recordable incident rate and the near-miss frequency rate, for both their direct employees and their contract employees. This ensures that a rock-solid safety culture protects every single person stepping onto that site, no matter whose payroll they happen to be on. Because a high incident rate, it isn't just a tragic human cost. It also triggers major regulatory penalties and grinds productivity to a halt.
Part 4. Innovations and Market Realities, Building the Future.
So, where are we heading? While traditional construction materials have historically relied on incredibly high energy usage and the relentless non-stop extraction of virgin raw materials, but the market is definitely shifting. We are seeing a huge rise in sustainable materials. These are products specifically engineered to drastically reduce upstream energy and water impacts, substituting virgin rock with secondary or recycled materials. And here's the kicker. This isn't just good for the earth. Requiring less processing inherently lowers production costs over the long run. It's a win-win. Re-engineering these foundational materials is actually opening up massive new revenue streams. The SASB standards specifically track the percentage of a company's products that qualify for green building certifications, like LEED or BREEAM. By creating materials that slash carbon emissions during manufacturing, or maybe provide better insulation once they're built into a structure, these companies can significantly increase their total addressable market share. It's a powerful competitive edge in a world where builders, buyers, and regulators are all demanding greener supply chains. The truth is, we are not going to stop building, but the way we build absolutely has to evolve. The operational footprint of extracting, crushing, and combusting the earth is immense. So as we look ahead to building tomorrow's infrastructure, how will we balance the massive volume of earth we physically must move with the fragile ecosystems and human communities we have to protect? It's an incredibly heavy question for a heavy industry, and the standards and metrics we've explored in this explainer today are exactly how we start tracking that balance. Thanks for joining us.